All right, AP 14.2, reaction rates. Okay, we're going to need some calculators because we're doing some math. First of all, reaction rates, what we just talked about in 14.1, it's the speed of the reaction. But now to do it quantitatively, it's the change that occurs over time. So what change in concentration over time? Time, little t, not capital T, because that is temperature. Okay, so little t. So what change occurs over time? So say we took a generic equation, A makes B, and there's two ways you can measure rate. First, concentrating on the reactant, because what happens is when you start with a reactant, over time, it disappears. Okay? I didn't say negative. I just said it disappears. So over time, you start to lose reactant. You still got reactant, but you lose it over time. The disappearance of A, so the rate of A. So when we write a rate expression, it's always concentration over time. So the change in concentration over the change in time. So what we do is we take the concentration, little f, which means final, and the concentration of initial, and then same thing, T2 minus T1, same thing, final minus initial. So instead of saying final minus initial, we have a symbol that we use, a triangle. And a triangle, just like in math, means change. Okay, so the concentration changes over concentration of time. But did you notice this negative sign? Okay, this negative sign means because it reminds us that rate is expressed in terms of disappearance. Okay, so that negative is there is because the reactant A is disappearing over time. Okay, but write this big font. Your answer, which is going to be the rate is never, ever, ever, Taylor Swift said it, never, ever, ever, negative. Never negative. Rate is always positive. You're going to see me say that about 3 or 4 more times. In the other side, the rate of appearance. Okay? Because remember, over time, I'm going to gain some products. Okay? Initially, I have no products, but as soon as the reaction starts, I'm going to gain some products. So notice we call it the rate of appearance. So the change in concentration over the change in time, but this is of the product, whereas this one was the reactant. Same thing, final minus initial, change in B over time. But notice that positive sign. That positive sign has to do with the product, B, and how it's appearing over time. Okay? But regardless, this answer for rate, okay, rate is never negative. So that answer and this answer, never ever negative. The most useful unit for concentration is molarity, big M, okay? We know that. So when we do the units of rate, these rates right here, the majority of time is M over S. You could see M over maybe like minutes. You could even see hours, okay? Majority of time we deal with seconds, but you could see different units for time, okay? So this answer right here would be M over S. And same thing, M over S. Notice my M for molarity is capital versus second is lowercase. Please try to make a difference in the sizes of your units because there is a capital S that's coming in chemistry. So let's take this graph. A makes B. Okay? Initially at time 0. So notice here we have number of moles and then over here we have time, but this time it said minutes. So at time 0, what do you have? Well, at time 0, I only have A. I don't have any B. Well, that should make sense. You haven't even started the reaction. So at time 0, only reactants are present. Okay? Since the reaction hasn't started. Okay? So at time 0, let's say instead of moles, I say molarity, I don't have any concentration of B. Okay? So then reaction starts. Let's focus on A, the red line. Okay? So moles of A over time. Notice as soon as the reaction starts, 10 minutes, and then 20 minutes, and 30 minutes, 40. What's happening to the moles over time? Well, the moles over time are decreasing. I'm losing moles over time, and why? Because look at line B. B is the products. Over time, as soon as the reaction starts, I'm gaining B, and I'm gaining, and I'm gaining, and I'm gaining, and I'm gaining. All right, so over time, it increases. But what do you notice about the rate? So notice A and B, they're kind of like the same lines, just inverted of each other. Over time, what happens to rate? It actually decreases. It gets slower over time. So if it actually stayed constant, so like for A, you would actually see like a diagonal line, okay? Or actually for B, let me do B instead. Over time, you would actually see it goes up, 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 up. But notice what it does, it curves. It actually slows down as the reaction occurs. So where is the fastest part of the reaction? The fastest part of the reaction is actually in the beginning. So over time, oops, some of my stuff disappeared. So what happens to the rate over time? Slows down. However, initially, okay, the rate is fastest. That means the reaction is fastest in the beginning. Okay, so if I had to highlight where the fastest part of my reaction is, it's probably about right here and right there. So probably those first two, that first 10 minutes, 20 minutes, that's the fastest part of the reaction. Okay? So how do you do this with math quantitatively? All right, well, let's first look at this. This is what I started with. This is initially, okay? The law of conservation. Your favorite law. Okay? Whether it's mass or matter, okay? You can't create or destroy matter. You have to rearrange it. So matter and mass is rearranged. But remember, it has to be in a chemical reaction. So if I started with 1 molarity, when I add these two up, it's got to equal that 1 molarity because that's what I started with. So over time, 10 seconds, even though I'm going to change that to minutes because our graph said minutes. Okay. We have now, after 10 minutes, I went to 0.74 molarity. That means I lost some A. Well, then who gained it? B gained it. So now I'm going to take that 1.00 minus 0.74, and I actually have a concentration now of 0.26 molarity because both of these numbers have to equal that 1 molarity in the beginning. So 74 and 26 has to equal the 1. Well, where students go wrong, it's the next 20 minutes, okay, the next 10. So now from 10 to 20, I lost some more, but I gained what I lost. Regardless, these numbers have to still equal that initial value, okay? It's not equaling the 74, okay? You still have to keep in contact with that both of them equal that 1 molarity. So if I take that 1 molarity minus 0.54, I'm going to get 0.46. Okay? And if you notice these data points, look right here. So after 10 minutes, look right there, 74 plus 26. And the next 20 right there, 54 and 46, okay? And these ones right here, okay? Everybody has to equal that 1 molarity that you had in the beginning. So you can't destroy matter. You have to rearrange it, okay? So whatever you start with, both values have to equal that starting concentration. Well, now let's calculate the rate of A. So notice in the rate of A, okay, so remember our rate, okay, so rate of A, it's going to be A, because remember A is disappearing over time, the change in concentration of A over the change in time. Okay, so remember that change is final minus initial. So I'm going to concentrate on my A, and I want to go from 0 to 10. And like I said, I'm going to fix this. We're going to say 0 to 10 minutes. Okay, so my rate of A, negative, and I'm going to put these in brackets, because remember, brackets means concentration. Okay, so we're going to make a note of that so we don't forget. Brackets is concentration. Okay, I got to take final minus initial. So final was at 74. Remember, I'm going from 0 to 10. 0 to 10, so 0.74 molarity minus 1.0 molarity. Over time, same thing. Final was 10, 0. And I'm going to put a decimal because we don't like 1 sig fig. So I'm going to put decimals on those two. Minus 0. Well, I don't think we need a calculator for the denominator, so that's going to be 10 minutes. But now that's 74 minus 1.00. And I'm going to get that negative still in front. But notice this is a small number minus a big number. I'm going to get now negative 0.26 molarity. Now, why is rate always positive? Because remember, you put it up here, rate can never be negative. Heck, let's even highlight after you wrote it font 100, okay? Rate is never, ever, ever negative. This is why that negative is right there in the front, because the negatives will cancel. So when I take that 0.26 divide 10, my rate of my reaction is going to be 0.026 m over minutes. Okay, I'm keeping the 2 sig figs going. So 0.026 molarity over minutes. Now, I want to prove something to you. Remember I said in the beginning of the reaction is the fastest. So what happens to rate over time? It slows down. So over time, rate slows down, which means the rate will be slower over time. Okay, so let's actually prove that. So from now, let's do rate of A from 10 minutes to 20. So now let's look at from 10 to 20, same thing, the 74 and the 54. So my rate of A, this time I went to 54 final minus the initial. If I said from 20 to 0, then I would have picked that 1 molarity, but I said from 10 to 20. Okay, over 20 minutes minus 10 minutes. Okay, well, the denominator is still 10. But now, the top part, 0.54 minus 0.74, I'm going to get negative 0.20 because of sig figs, but don't forget that negative. And that's how the negatives will cancel to where rate will be positive. So 0.20 divide 10, and notice what happened to the rate. 0.020 m over minutes. Sorry, I crammed that in there. Oops, let's be boxing our answers. Okay, look at what happened. From here to here, the rate slowed down after another 10 minutes. Okay, so the reaction will just get slower and slower and slower. So if we did the next 10, will be even slower over time. Okay, well, let's see what happens to B over time. Okay, so we have our values above, right up here. So I'm going to put our values here. Initially, at time 0, we don't have rates at time 0. So these should be blacked out. So from 0 to 10, our rate was 0.026 molarity over minutes. And right here, 0.020 molarity over minutes. Okay? Well, let's see what happens to B. But for B, we want to concentrate on the B line. Okay? So only these values over time. Okay? So from 0 to 10, I have 0.26, and remember initially I started at 0, okay? So let's actually, there we go, so that way we can see our data. There we go. All right, so right here from 0 to 10 minutes, and I promise I'll fix that for you guys, minutes, okay? So the rate of B, okay? Now it's appearing, so the change in B over time. So that positive that's in front, because remember, it's a product. It's appearing over time. So I'm still going to take my final minus initial. So my 0.26 minus 0, because I didn't have anything in the beginning, over that 10 minutes. Well, I don't think I need to show 10 minutes minus 0. I think we got the point, 10 minutes. But if you need me to show it, it's right there. Okay? All right, so 0.26 minus 0, well, I'm still going to get 0.26 molarity. Over, 10 minutes. Don't mean that decimal there. 10 minutes. So 0.26 divided by 10. And I want you to see something. Look at what we just did for A. Go back up here. Look at that. Let's highlight it in blue. Rate of A, 0 to 10 minutes, disappeared at that rate. Well, rate B appeared at the same rate. So what do we notice about rate? Well, the rate of A is equal to the rate of B over time. This is why you have an expression called the rate expression. So over time, rate is not constant. It will decrease over time. But the rate of A will equal whatever the rate of B is at the same time interval. So if you're looking at 0 to 10 minutes for A, so I'm going to put right here, time from 0 to 10. Same thing here, time 0 to 10. They will equal the same. So what do you think the rate of B is going to be? Probably what A did from 10 to 20. From 10 to 20, I bet you the answer is going to be 0.020 m over minutes. Well, let's check it out. From 10 to 20, so my rate of B, I'm going to take my final, which was 46, minus my 26. And I'm going to take 20 minutes over 10 minutes. Okay? Well, we know the denominator is 10. I don't want you to think it's always going to be 10. It just worked out this way in this problem. So 46 minus 26, and look right there. It's going to be the exact same thing as that 0.20. And 20 divided by 10, and there it is. Okay? I like to put the plus sign in front of it to remind me that that plus sign means it's appearing, and the minus is disappearing, okay? So conclusion, rate is always positive, no matter what, okay? But it's not constant. It will decrease over time, which means it gets slower over time. Oops, not of. Okay? So we have something called a rate expression using stoichiometry, okay? So let me get to this last part. What happens when you have actual coefficients? Notice in the example above, our A to B is a 1-to-1 ratio, okay? That's why, I'm going to put it right here, rate of A for our experiment, A to B. The rate of A and B equal each other at the same time interval. Here's the next part. If the moles are the same for A and B. What if the moles are different? So how does stoichiometry affect rate? Okay, so let's say we have this generic equation. A plus B equals C and D. Well, the little letters are the coefficients, okay? The capital letters are the actual chemicals, okay? So when you write a rate expression, you're trying to show how all the rate of all the reactants equal the rate of all the products over time. So right here, I have negative, the change in A, because remember, these guys are disappearing over time, so you have those negatives. And the A would be whatever the coefficient is, okay? If it's a 1, you don't have to put anything. So the change in concentration over time. And then B, because he's a reactant, change of B over time. But then C and D are appearing. C over time and D over time. The only thing that makes it different are these coefficients. But we didn't deal with that in the problem above because everything was 1-to-1-to-1. So we call this a rate expression. It's comparing how the rates of reactants and products change over time, okay? Because everything was 1-to-1-to-1, the rate of A equals the rate of disappearance of B and equals the rate of C and equals the rate of D. Why do 4 calculations if they're all the same coefficients? They're going to all be the same rate value. Whatever that value is, whatever that number is, molarity over seconds or minutes or hours. But you know in chemistry, life isn't that nice. What if something isn't 1-to-1? So let's say we had this generic equation. My 2 reactants produce 2X and a P. So for every 2 R's that are disappearing, for each 2 moles of X, and a mole of P that form, will the rates be the same? Well, because I have a 2-to-2-to-1 ratio, the rates won't be the same. Of the chemicals above, who actually would have the same rates? Well, the rate, because I have a 2 and a 2, the rate of R would equal the rate of X, but what about P? They wouldn't. So would not equal the rate of P. What would be the rate of P? Well, it would be half as fast as R or X, okay? Because of that coefficient, okay? Because of that P right there, and I'm going to fix this. I didn't mean to put hydrogen here. P right there, you actually have half the amount. You only have 1 mole versus 2 moles versus 2 moles. So that rate right there will be half as fast. So when you write a rate expression, okay, that 2 for the reactant, you just put it at the bottom, and that should say R, okay? And then this X, because remember, they all equal each other, that X right there, you put the X right there, but then you put a 2 in the denominator because of the coefficient. And then that P, well, I have a coefficient of 1, so then it's just a 1. Do you have to write the 1? No. Okay? So as that is disappearing, X is appearing, and P is appearing. This expression is very misleading. Okay? So this is called rate expression. However, between me and you, I'm not a fan of this expression because it's misleading. It makes it seem like because these values are divided by 2, it makes it seem that P is faster, but it's not. So this rate expression, okay, beware, okay? P looks like it is 2 times faster since R and X have a 2 in the denominator. Okay? And that makes it look like it's half as fast. So looks like P and X are half as fast. Not true. Not true. Not true. So here's Rodriguez. Okay? Only look at the balanced equation to determine which chemical has the fastest rate. That's all you need. AP makes us teach you this expression. I think it's pointless. I don't like this expression, but I got to teach you, okay? Because I'm going to teach you the stoichiometry way, but I have to teach you how to write it, okay? So this is called rate expression. Be very careful in this next video. Something called rate law is not the same, okay? So one more time. R and X, because you have twice the moles, R and X have the same rate. However, P does not, because of that 1 mole, it is half as fast. And why? Because 2 moles versus 1 mole, who has the more collisions? 2 moles. More collisions. It always comes back to collisions. 1 mole, less collisions. Okay? Always go back to collisions. Let's do an example. I want to show you an example where I do this, but I do it stoichiometry. Let me go back to the graph real quick. Notice right here, 2 moles of R. Well, R is the blue, so this is your R right there. It's decreasing over time. So notice that slope right there. That is the fastest rate is initially. Okay? And then notice P, the product, is this red line right here. So I'm going to put P as the red one. Okay? And then X is this yellow one. Okay? That's X. Well, remember, these guys are appearing over time, so they have a positive slope, whereas what R is disappearing over time. But notice X and P. Why are X and P at 2 different? Because remember, P right here is 2 times slower than X. X is 2 times faster than P. Okay? But what about R and P? Okay? This and this, whoops, have the same rate over time. Okay? So, remember, rate is the fastest in the beginning, but over time, rate decreases. Gets slower and slower. Okay? So let's do an example. I have a whole bunch of ions and a whole bunch of coefficients. Okay? Let's say the rate of disappearance of Br, so we're looking at this guy right there, Br negative. It says that the rate is 3.5. Let's get out of this yellow color. Okay? So the rate of Br, so that guy right there, is 3.5 to the negative 4 m over s. Okay? Seems pretty slow. But how does it compare to Br2? Okay? So we're going to do this guy in red. I like stoichiometry. Stoichiometry always works for me. So if I start with 3.5 times 10 to the negative 4 m over s of Br minus, well, use stoich. I'm not trying to get rid of, because I want rate. I'm not trying to get rid of the units. I still want m over s. I just want a new chemical. And how do you change chemicals? Well, you need stoichiometry. So right here, I have 5 moles of Br minus, and I have 3 moles of Br2. I got rid of the moles, but now I got rid of the chemical. Okay? Now, before you plug and chug, think, will the rate of this Br be the same as Br minus? No. These two rates will not be the same. And why? Because the coefficients are different. The only way they would be the same rates is if they both would be 5s or both would be 3s. So then who would be fastest? Well, this Br minus is going to be fastest because why? More moles. And this Br2 is going to be slower because it has less moles. Okay, so let's plug it in. So 3.5 to the negative 4, and then times 3, and then divide by 5. And there you go. See, it's slower. 2.1 times 10 to the negative 4. Okay? Just a little word to the wise. Don't forget when you're plugging in scientific notation, okay, hit that E button, 3.5, E button, negative 4. Okay? Let's try another one. Same equation, but let's find a different chemical. What's the rate of disappearance of hydrogen? Okay? I'm looking at, we'll go a different color. Let me erase those. We'll go maybe, let's go blue. So I want to look at hydrogen, but I said disappearance. And why did I say disappearance? It's because it's a reactant. However, will your answer be negative? No. Rate is still positive. Okay? Still positive, people. All right, so first, will the rate of Br minus be the same as H plus? 5 versus 6? Nope, not the same. But who will be faster? Well, it's only one more mole, but this will be faster, which means it will be a greater answer than this 3.5. So let's use the same number, 3.5 to the negative 4, m over s, and Br minus. I'm just trying to get rid of the chemical, so I still got 5 moles. And then I have 6 moles. Bye-bye moles, bye-bye chemical. So now plugging it in, 3.5 e to the negative 4 times 6, divide by 5, and it's bigger. It's faster, 4.2 to the negative 4, m over s. Oops, I need to put my H plus in there. H plus. Okay? All right, hopefully you're getting the hang of this. What if I want one more disappearance of the other reactant? Okay? Well, let's go green. Let's go green. Disappearance of BrO3. So I'm looking at that guy. Okay? So, first question, will the rate of Br minus be the same as the rate of BrO negative? Not even close. Okay? This Br minus is going to be 5 times faster. Or think of it as this BrO3 is going to be 5 times slower. Okay, so let's prove it. 3.5 to the negative 4, M over S, Br minus. Same 5 moles on the bottom, and I only have 1 mole on top. 5 by mole, oops, and chemical. Didn't mean to get rid of that chemical. Oops, get rid of that line. All right, 3.5 to the negative 4, divide 5. It's going to be slower. Beyond slow, and we need 2 sig figs. So 7.0 to the negative 5. And don't mean to crunch it in there, but BrO3 negative. Nah, that's ghetto. I don't like that. Don't do that. Don't do that. It's because I just write so big. BrO3 negative. Oops, there you go. So remember, when you're comparing exponents, negative 3 is larger than negative 5. Okay, so this rate was 5 times slower. Okay, hopefully that was helpful, AP. But beware, 14.3 rate law is not a rate expression. See you on the next one.